Welcome, ladies and gentlemen, to this video lecture. Okay, let's take a look at this example. So, determine the average value of sine on the interval from 0 to 2 pi and find a point P in the open interval from 0 to 2 pi so that the function value of sine at P is equal to the average value, if it exists, if such a P exists. So let us determine the average value of sine. So the average value of sine is the integral from 0 to 2 pi over 2 pi of sine x dx. And I will leave that as an exercise. You will see that that is equal to 0. You can also think of why that should be. The graph of sine looks like that. This lobe cancels with that lobe, so the average value is equal to 0. And we see here at pi, there exists a point P in the open interval from 0 to pi, where the function value is equal to the average value. And we've got sine of pi is equal to sine, or the average value of sine. So we see here we actually have, there is a function value which takes on the average value. Let's take a look at the next example. So here we've got a function f, which is defined piecewise. So f is defined on the closed interval 0 to 2. It is defined to take on the value 3 and 0, 3 on the unit interval 0, 1, and 0 on the interval 1 to 2. Determine the average value and find some p in the open interval 0 to 2 with fp equal to the average value. So let us determine the average value. So f average, that is 1 over 2 integral from 0 to 2 of f of x dx, but that is the same as, or shall I leave that as an exercise? This is equal to 3 over 2. Okay, but now we should notice, if we think about what this function looks like, it takes on the value 3 there, takes on the value 0 there, and 3 over 2 is here. So there is no p in the open interval from 0 to 2, which actually takes on the value 3 over 2. So there exists no p in the open interval 0 to 2 for which f of p is equal to f av, which is 3 over 2. Okay, so we see here sometimes the function, there is a value or a point in the domain of the function at which the function takes on its average value, and sometimes not. And what is the difference between these two functions? So the difference between these two functions is, well, first of all, sine is continuous, and this function f in this example is not continuous, has a discontinuity at 1. So perhaps continuity is a sufficient condition for the function to take on its average value. And this is the theme of the next theorem that we will discuss. So theorem, and this is what is called the integral mean value theorem. So the integral mean value theorem. And we will actually use the differential mean value theorem to prove this. So let f be continuous on a closed interval. So let f be defined on a closed interval AB, and let it be continuous. Then there exists some point P in the open interval A to B, so that f of P is actually f of P is equal to the average value of f over the interval AB. Okay, and let us prove this. So, proof. Let us define big F on the interval AB. And how do we define big F? We define it as the integral from a to x of little f t dt, with x in the closed interval AB. Okay, so since little f is continuous, by the fundamental theorem of calculus, big F is continuous on the closed interval AB and differentiable on the open interval AB. And we also know what its derivative is on AB, and the derivative of f is just equal to little f on for x in the open interval. So for x in the open interval. But now, by the differential mean value theorem, so by the differential mean value theorem, this is theorem A.1.9. Just recall what the differential mean value theorem says. If you've got a function that is differentiable, and you look at its graph, and you look at its endpoints, and you look at the slope, what you that you get when you connect oops, that's not what I meant. When you connect the endpoints of the graph and you look at the slope of this line connecting the endpoints, then there exists a point in the open interval which has exactly the same slope as this line over here. So that is what the differential mean value theorem says. Okay, so by the differential mean value theorem, there exists some p in the open interval AB, so that the derivative of fp is equal to, now the slope of the line connecting the endpoints of the graph of big F. But if you now work this out, this is f of b integral from a to b of fx dx all over b minus a, and minus the integral from a to a of whatever, but if we integrate from a to a, that's just 0. So we see this becomes the average value of f, but what is the derivative of big F? That is just little f. So here we see there exists a p, so that the function value of little f is equal to the average value of little f on the interval AB. And that is exactly what we set out to prove. Okay, I will see you in the next one.